Our next goal is to present a test that is called a comparison test. The idea is the following. Let's say we are trying to classify the series I wrote over here. So we have the sum from 1 of the expression 2 over 3 to the power of n plus 1. The idea here is that we may notice that this is kind of similar to this other series, 2 over 3 to the n, summing from 1 on. Well, they are similar in the sense that they are just like the difference is plus 1 we have in the denominator. But the second one I wrote over here, this is actually a geometric series. And the ratio is 1 over 3. So it's convergent. So we would like to see how we can use the convergence of this series I wrote with blue to actually classify as convergent the original series. The statement of the test is the following. Let's say we have two sequences, an and bn. They are both positive and an is less or equal than bn for all the terms after some point that I call capital N. Then, if we know that the series associated to the larger one converges, then the series associated to the smaller one converges as well. And if we know that the series associated to the smaller one diverges, then the series associated to the bigger one has to diverge as well. I think this is a very intuitive result. We know that some terms are big, but the series is still convergent, then the terms that are not that big also form a series that is convergent. If we know that the terms an form a series that is divergent, then the terms bn that are even bigger, when they form a series, it also has to be divergent. Let's see how this applies to our example here. Let's look at the sequence 2 divided by 3 to the n plus 1. All those terms are obviously positive, but even more, they are less than 2 over 3 to the power of n, because we don't have the plus 1 in the denominator. When we make larger the denominator, then we make it smaller the fraction. Now, this has an associated geometric series that, as we mentioned before, converges. Then, by the comparison test, the series that we were trying to classify is pretty much the same, but with a plus 1 in the denominator, also converges. And that's it. We classify the series we wanted to classify. Now, this test is relatively easy to apply, but what we have to be careful is that it cannot be applied in all kind of situations. We have to be careful with which direction we have the inequalities pointing. Let me give you an example, kind of, well, not very mathematical, but explains how this works. So we have over here two students. It's called student A and student B. Let's say we know that student A is a good student. And let's say we know that actually student B is better. So we can conclude that student B is a good student as well, because it's even better than a good student. So that will work. But let's say that we have over here another student that I'm going to call student C that is not as good as A. Now we know that A is good, and we know that C is not as good as A, so we cannot conclude anything. It could be that C is good as well, just that A is better, or it could be that C is not a good student at all. So we have to look at which direction the series are pointing. If we know that the larger series is converging, then one that is smaller, also with positive terms, of course, it's also convergent. But if it's one that is even larger than a convergent one, we cannot say anything about it. So now that I told you how to be careful with the inequalities, let's apply a couple of times more this very useful test, and we're going to apply it to classify the series associated to 1 over n factorial, summing from 0 and on. Let me just write the first few terms we are trying to sum over here. So that's going to be for n equals 0, we're going to have 1, and then we sorry, mess up here. I say 1 plus 1, and then we're going to have 1 over 2 times 1 plus 1 over 3 times 2 times 1 plus 1 over 4 times 3 times 2 times 1, and so on. The n term we are summing over here as n times n minus 1, so on, times 1. And we keep summing like this. We are going to compare this to the following geometric sequence. The sum of 2 times 1/2 to the power of n, and we're going to start summing 0 as well. So the first term we're summing is 2, then we have 1, then we have half and a fourth, and like this. Note that the series that we're considering, the associated sequences, they have only positive terms. And after this initial term for n equals 0, where we actually have 2 for the geometric series and 1 for the other one, after that, we have that the terms of the factorial one are always less or equal than the terms of the geometric one. So we have the situation that 1 over n factorial is less or equal than 2 times 1 over 2 to the n, and they are all positive. And this is true for n greater or equal than 1. But this geometric sequence we are considering over here, the associated series, is convergent because, well, the ratio we are considering is a half, so in absolute value is less than 1. So by the comparison test, CT, the series with the factorials that we wanted to classify, summing from 0, also converges. Note that even more, for the geometric series we consider over here, if we want, we could even find the sum, and this will give us, we have a formula you can write, give us 4 as a result. So what we have over here is that the sum of the series we classify as convergent is going to be less than 4. And later on, we're going to see that actually we can find the exact value, and it's the value E. Let's look at one example more. We wish to classify the series with general term 1 over 3 plus square root of n. We may be tempted to try to compare it with the series that has an associated term 1 over square root of n, because, well, it's kind of similar. We just have a plus 3 over there. And also this one over here, if we look at the series, this is the P series with P equals to 1/2. So this one diverges. So we like to compare it because there's only this plus 3 over there bothering us. So we like to compare it to a divergent series. But actually what we have is that this general term 1 over square root of n is greater than 1 over 3 plus square root of n. Yeah, and well, they are all positive. And that's because we are just summing a 3 in the denominator, making the resulting fraction a bit smaller. But the problem is, knowing that the bigger one diverges doesn't tell us that the smaller one is divergent as well. So we need to, well, following the same idea, try to compare it in a more smart way. So what we like to see is actually another series so that we can make sure that it's divergent, but we can put it over here between 0 and the terms of the series we're trying to classify. So we want here the n term of a divergent series. So we can apply the part B of the comparison test. So what about trying this? Let's say we look at square root of n, and we know that this is going to be greater than 3 if n is greater than 9. So that means if we look at square root of n plus square root of n, this is going to be greater than 3 plus square root of n for n greater than 9. But then if we consider the reciprocals, 1 over 3 plus square root of n, this is going to be bigger than 1 over 2 times square root of n for n greater than 9. So this is the general term I want to fit over here. 1 over 2 times square root of n. And again, this is just a little modification on our p series for p equal 1/2. Just multiply by 2 the denominator in each term. And then since 1 over 2 times the square root of n, summing from 1 on, since this one diverges, then the one we were trying to classify that has a plus 3 over in the denominator, this one also diverges. Now, sometimes it's a little bit annoying to fit the series we want on the correct side. So we're going to see a little bit of a shortcut to this, and it's what is called the limit comparison test. So we're going to see that we don't have to really look at which one is bigger and which one is smaller. As far as n approaches infinity, the n term that we are considering, they are basically the same other than the presence of a constant. So this is the statement of the limit comparison test. We have two sequences, an and bn, with positive terms, both of them, at least after some term capital N. And then the result we have is the following. Let's say that we look at the limit as n approaches infinity of the quotient between the sequence an and the sequence bn. If that limit is L, when n is a finite and positive number, then the series have the same behavior. They both converge or they both diverge. If the limit is 0 and the one in the denominator converges, then the one in the numerator has to converge as well. And if the limit is infinity and the one in the denominator diverges, then the one in the numerator has to converge as well. This is very useful for, well, many cases, but for instance, when we were looking at the series in the last example, that we had 3 plus square root of n in the denominator, we can look at the limit as n approaches infinity of the terms 1 over 3 plus square root of n and 1 over square root of n. We know that the sequence in the denominator is associated to a series that is convergent. And when we are looking at this limit over here, let me write a little bit more. So 1 over 3 plus square root of n times square root of n. Well, the limit of all this is just going to be 1. This 3 over here is not going to be relevant as n approaches infinity. Then from part A, since we know that by the p-series test that 1 over square root of n converges, then the one with the 3 being some in the denominator converges as well.